almost everything in this folder. We're going to look at threads with callbacks. Mr. Wang, I think it was, asked me about callbacks, and so generate a little example. You can't see this, but these are, if you pull this up on your laptop, you'll see that blocking queue and thread test and thread pool are shaded but a different color. They're shaded because they're important. They're a different color because I won't ask details about that on the midterm. Threads are fair game, simple enough, but these are the next click more complicated, you know, and so I'll probably talk about thread pools, but you will on the exam be expected, you will be asked to write at least one question will ask you to write threading code. At least 2 questions will ask you to write code. And there'll be questions about principles. Okay, so all that stuff I keep telling you, gonna be on the midterm. Guess what? It's on the midterm. Okay, so let's start out with C++ 11 concurrency. So I want to start with basic threads. It's real simple. Just exactly what we talked about in class, and let's set this as startup. So I have a function called hello that declares a static mutex. Can you see that in the back? Okay. This projectors aren't super. I tried using the light view and it gets washed out. I think this is easier to see, but so if anybody can't see, you know, speak up and I'll make the font bigger or something. So I have a function hello. This is what the thread is going to run, and it has a static mutex. And the way statics work, the first thread that enters this function creates that mutex, and this statement is never executed again. Because it's static, that mutex is shared by every thread that enters this function. Okay. And if you're going to lock something, if you're going to protect some shared, if you're going to take some shared resource and make access to it serial, that has to be through a shared lock. If I have 3 threads and they each hold their own locks, there's no locking at all, because they automatically acquire it because they're the only one with a lock. Okay, so it has to be a shared lock. So this is one way to do it. Make it a static. You know, if there's only one function being called, perfectly good way to do it. And I'm looping here 5 times, and all this lock is doing is making sure that these 2 insertions happen one after the other. If I didn't have this lock, nothing bad would happen, but I might get 2 threads that would insert this first, and then the first one come back and insert this one, and then the third one insert this one, and then the second one, you know, it would get all mixed up. I'll illustrate that for you. And then, so now I just start the 3, hello, 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 and away we go. So now I join, and I must either join or detach a thread before I leave. If I don't, an assertion is thrown. Unfortunately, it's not an exception. It's an assertion, meaning you can't catch it. You can't embed that in a triangle. I'm going to show you that you can't in a further example. So okay, Rohit, I raised it up a little bit so you can see it. Okay, so let's just run this, and it says hello, hello, hello. Okay. And so here, I didn't get any interleaving, but this morning, when I ran it for the first class, there was a little bit of interleaving. It's just indeterministic, you know. If I, let's just try removing this lock. So let me, well, okay, so. So now let's run it. So you see it's getting a little garbled up. This guy didn't appear until down here. That's all the lock is doing. All the lock is doing is ensuring that those two insertions happen together. That's all it's doing. Okay. All right. So now let's look at thread parameters. So now I want to pass parameters. So I've got this function hello that now takes an integer. This is the ID of the thread. So the example is exactly like before, except that instead of using the thread package's ID number, I'm going to give it an ID number, my ID number. Instead of 6688, it's going to be 1. Okay. So I give it those IDs, and now all I have to do is say T1 hello arg, and if I had 3 args in a function, I would just 3 args. I'm going to show you how this works very close to the end, how these functions work, how that accepting a number of arguments works. So anyway, let's run it, and so so now I'm passing arguments to it. 1, 1, 2, 2, 2, 3, 2, 3. So good. So now we know how to pass arguments to the thread. So now let's see what oh yeah, let's go look at asynchronous methods before we move on. I've shown you using unbound global functions as the thread function, but now we're going to use a member function of a class. Okay, so I have this class, same message, and it's got a function say, all right, and what happens is I'm going to give this constructor an addendum, something to add to the end of what's passed to the what the thread passes in. So this is the main message. I'm sorry. So in say, it gets a message, and the constructor just gives it an addendum to add to the end of the message. And so now, when I run it, I say, the first argument is a function pointer for that method. The way it works is you say, this is a class name colon say, that's the name of that member function, its address. And now I have to pass the address of the object I want to apply that to. And obviously these have to be from the same class. Okay. And now my messages. Okay. So this is the argument I'm going to pass to the thread. And so now my message and addendum. Okay, it works. Piece of cake. So it doesn't matter whether it's an asynchronous method or not. So now let's look at concurrency. The example named concurrency. So here I have a thread proc, and I am passing in, this string will be shared by all the threads. This is, each thread has its own ID. And this is a time that thread's going to sleep. So what happens is I come down here, I have just like before, I have a shared mutex, shared lock, take the lock, and now I'm incrementing, I am appending the ID to the shared string. So I'm building the string. So each thread is appending its own ID to the string. It starts out empty, and so it's just going to be a string of IDs. Okay, we're not going to see the result until the end. Okay, because if I print it out every time around the loop, you'd see this cascading growing down. Okay, so but we'll just do it this way. So now I say thread T1, thread proc, standard ref shared. Here's the ID I want you to append, and here's the wait time. So I'm getting them to interleave by changing the amount of time they sleep. Why is the standard ref? The thread function passes all its arguments by value with good reason. Because if a caller sat there and tinkered with one of those arguments, they could have a race condition with what the thread was doing if it was passed in by reference. Okay? Guaranteed subtle bugs with race conditions if they did it. So they wisely chose to pass it by value. But now our goal is we want all the threads to share the same string. So we create this shared string here and we pass it in by reference. We're not going to touch it. Okay, so it's our obligation, having done this, not to touch that string while the threads are running. But so we pass it in by reference, and each one of the threads are appropriately locking it. Okay, I could handle that string if I not only passed in the string, but I passed in a mutex, and I, as well as all the threads, shared the same mutex. I could do that. But because I put the mutex in the thread function, I won't share that mutex, and so anything I would do to that string is dangerous. So anyway, shared reference, blah, blah, blah. Now, I'm going to illustrate some things that happen. So here, you can get a thread to return a C++11 thread object to return the native thread handle, the handle to the native thread that it's wrapping. And that's what I've done. And now I'm waiting on multiple objects for that. And I have a point for doing that in a minute. I display the string. And now, if T1 is joinable, detach. If T2 is joinable, detach. If T3 is joinable, detach. Okay. And so what's happening? What's happening here is I am making sure before I leave this function that I am calling detach. It isn't just a question that I need to wait for the thread to finish. Okay, that isn't enough. Not only do I have to wait, I may not wait for the thread to finish, and nothing bad happens as long as I've detached it. I'm going to illustrate that in a minute. But anyway, let's run this. For the minute, I'm waiting on it. And now detach doesn't wait on anything. It just disassociates that thread from the so here's my 1, 2, 3, 1, 2, you can see it's kind of interleaving. So each one of these threads are just marking that, adding their own ID to the end of the thread and so on. Now, let's see what happens if we don't wait. No exceptions. I detached them all. So when my console exited, I've got nothing to keep the console alive. I just execute my statements, and when I terminate, those threads are still running. They're detached, but they're still running. Nothing bad happens as far, no exception. The C++ thread class is not going to assert, okay, because or throw an exception because I detached it. So it's perfectly happy. I just didn't give it a chance to finish. Now let's do it the other way. Let's give them a chance to finish, but not detach. So now let's give them a chance to finish. By the way, this leading : is here. That's totally unnecessary. I do that to remind myself this is an API function, this is a global function. So that's all. So now let's just remove the detaches. Let's just remove the detaches. Let's just not detach the last one, just for fun. But we're waiting. Huh. Oh, it didn't. Yeah, sure. I selected it, but I didn't. Thank you. I didn't. That's what happens when I get up here and talk. And so now we're not going to detach that last one. Bam! Angry. Debug error. Assert. Why, why they don't throw exceptions. I think that's an assert. It's possible that there's the C++ library, but I think not. I think this is an assert. So let me put that back just so the next time I run this I'm not confused. So you've got to either join or detach. And the reason I just waited on these handles was to show you that, what happens if I detach them, just so I could show you. So anyway, now let's look at thread lifetime. I think I've really said most of, I forgot that this was here, and I think I said everything I want to. Yeah, let's take a quick look at this, but I don't think I'll even run it. This is just a hello function, and now here I start a thread T1, but I don't give it anything to run on. Perfectly valid thread object, but it has no underlying operating system thread. It's just like I had detached it. Now, the only way for me to make this thread runnable is to assign it, to create another thread and assign it to it. And that assignment is a move assignment. You can't copy assign or copy construct threads, but you can move assign them and move construct them. So what I would be doing in that case if I said standard thread T1 equals some already, But anyway, now this I'm not going to join or detach, so that would throw that nasty assertion. Here I join it, no problem, and here, I'm doing just what I did before, and this was the example I meant to demo what I did, but we've already been through that with the other ones, so. The only new part about this is that I can create an empty thread, and it'll never do anything. And by the way, I don't need to detach or join it because it's not joinable until I give it a thread to run on. Okay. So. Okay. Now let's take a quick look at atomics. So atomics are support incrementing and decrementing integral types. A short, an int, a long, a pointer, all those are integral types. And I can increment them and decrement them, load and store them atomically. And this plus operator is an atomic operation. Not all of the operations associated with atomic class are atomic. So you need to look at the docs to see which are and which aren't. But the increment and decrements are. Now again, I'm using this lock guard not because of the atomic, just to make this these two insertions happen together. Okay, but here, load, this is an atomic load from memory. Okay, so, and there's an atomic store, the same thing. So now, and I can ask, is this lock free? If the operating system if the platform provides an atomic, the C++ thread class just wraps the platform atomic. But if the platform doesn't provide an atomic, then it uses locks to build its own. Okay, and locks are slower. So, do I want to use an atomic? Yeah, I might want to test it to see if it's lock free, and if it isn't lock free, do something else. But anyway. So, and all I'm doing is I've got my thread here is incrementing this count 20 times, and my main function is decrementing that same count. Okay, this is a shared count, but I don't have to lock it because it's atomic. It's decrementing it 8 times. So I should have a net of 12 when I'm done. Right? The thread trying to push it, increment it 12 times from 0, 20 times, and the main thread trying to push it down. So they're going to fight each other for a while. Okay. So let's see what happens when we run it. So sure enough, here they are fighting each other for a while. Bam, 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 bam. I want it up. No, I want it down. No, I want it up. I want it up. I want it down. Okay. But at the end, it's 12 because, so hey, that worked. And I also show on Windows platform, the atomic is lock-free. I suppose it could be possible that an atomic pointer wouldn't be lock-free. I don't know, but
Professor?
Yes.
Can you explain more detail about atomic? I don't know what's atomic.
Atomic means that guaranteed not to have a race condition even though I don't use a lock. It means that operation happens atomically. It means, in other words, that it looks like it's a single operation even though under the covers it's a load and store. It's a load, it may be a load from memory and then push into a register or something like that. Okay, so atomic means that I can't get partway through the operation, my time slice expires, and then another operation sneak in. Okay, and operating systems need to have atomic counters themselves because they're doing a lot of stuff with counters themselves with lots of threads running in the operating system. So they needed to have these atomics, and for a long time Windows didn't publish an atomic operation, but not for a long time, but at the very early days they did. Okay. Does that make sense? Did I answer your question, Hal? How's up? Dong Hal? Did I answer your question?
Yeah, that's okay.
Okay, good. Yeah.
Post increment also atomic. This is pre-increment, right? Which are showed in the code. This plus I is a pre-increment, right?
Increment is atomic, and decrement is atomic.
I mean, pre-increment and post-increment both two are different. Right?
Yeah, yeah.
Post-increment is also atomic.
I think so. See, the operating system, it's possible that it isn't. Possible that it is. You should look at the docs. cpbreference.com will tell you what's atomic and what's not. Okay. And not all the atomic class operations are atomic. So you do need to look at the spec. Okay. But I believe both pre and post are atomic, but I'm not, that's in my 80% certainty level. Okay, that's where I am. So, because I look for the cases I used, the pre, increment, and decrement. I looked, and it was atomic, but I didn't look for the post. And it's possible that it wouldn't be because there's a temp always when you post. There's a temp being created. So, yeah.
I'm not.
I haven't used. Beg your pardon.
Where do you, in the C++, where do you use the mutex unlock? You never use unlock in C++.
No, you use them. So, but here I'm using lock guard. So let me talk about, the next thing I'm going to talk about is lock guard. So defer your question. I'm going to talk about lock guards, and then make sure I answer your question before I leave this next presentation, okay? I will answer it. So let's look at lock guards. So here I have a function. I'm declaring lock guard. Now what lock guard does is, in the declaration, the constructor acquires the lock. The destructor releases the lock. There is no lock and unlock functions in lock guard. Basically, what it has is a constructor and a destructor. It may have some other fun, but it doesn't have lock and unlock. Okay. And so what happens here is, notice I have a dummy scope. These curly braces, anything with curly braces is a scope. So memory is being allocated for this scope right here. Okay. So here, I'm declaring, and that memory is just going to hold this lock guard, is all it's going to do. I'm declaring this lock guard here. So right here, the lock is taken. Now I do this output that has two insertions. That's why I want to lock it. Okay. And now the lock is released here. And now I sleep after the lock is released. The behavior would be different if I slept inside that lock, because I want to give these threads a chance to interleave. Okay. So now mutex doesn't work that way. So mutex you specifically call lock and unlock. There is also a standard unique lock that's a combination of lock guard and mutex. Unique lock has a constructor that acquires a lock, has a destructor that unlocks, that releases the lock, but it also has a lock function and an unlock function. So if you don't want to be bound by the scope, maybe you got a bunch of stuff going on in the scope and you just want to lock this one little area, instead of making a dummy scope, you can just use standard unique lock, and that works fine. And by the way, it does no harm if I lock an already locked unique lock, or if I unlock an already unlocked, does no harm. Okay. So the fact that I unlock it and then later on go out of scope and call unlock again, it does no harm. Okay. So mutexes we have to lock and unlock. Lock guard was specifically designed that you don't have to, you just declare it, but until it won't release the lock until the end of the critical section. So, and very often, maybe in the you got a whole bunch of code and only something right at the top needs to be locked, and you don't want to use lock guard because you'll have a whole bunch of code that's running inside the lock that doesn't need to. Oh, I mean, you could use lock guard and have a dummy, but it would be much better, cleaner. Just use standard unique lock. That's what you'd use it. And you would say, now, the difference between mutex and unique lock, there is a critical difference. If I throw an exception in code that's locked with a mutex, the mutex does not get unlocked. I don't release the lock. But if I throw an exception inside a unique lock or a lock guard, the destructor is called, and because any object, when an exception is thrown, any object, all the objects in that scope that have been created are destroyed. So that guarantees that the lock is released. So using a standard unique lock or lock guard is superior to using a lock, just because you don't have to remember yourself to do a try-catch around the mutex. So here, I'm just displaying the function that I'm in, so I, let's just run it and see what happens. So here, in test, in main, main, test, 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 main. And again, this lock guard is here just to keep those insertions together, but let's just remove the lock guards. Nothing bad will happen, it's just that the output will be a little garbled, maybe, depending on the timing. Okay, so here's test main. A guy stuck in ahead of it. So the first one was going to say in main, but he didn't get the main out before the second thread stuck in test. Then his main came. Okay, that's all. That's all I'm doing with those lock guards. Okay, so now let's look at did we look at concurrency yet? I think we did, didn't we? Thank you, Nog. So let's look at future. Back to the future. Michael Fox, are you around here? Where's the DeLorean? So most of you don't know what I'm talking about. Nag knows what I'm talking about. No? Well, there's a movie, Back to the Future, that starred Michael J. Fox, and the car. When they went to the future, they hopped in this car, and the car was a DeLorean. It was sort of like a Tesla in the old days. The company went bankrupt, but which Tesla probably won't do. So what am I doing here? I'm setting as startup future. So now, so here I have this say function, standard mutex, and now 25 times I'm going around printing a message number or something, and then I'm sleeping for some number of, and I'm gonna pass it the number of seconds I'm sleeping and this message, the string message. Now, notice that this function that I want to run asynchronously returns a value, a size t. Okay, it has this return type, size t, and what it's returning is the count, which is just the number of times it went around the loop. Okay, I mean, obviously I know what the answer is going to be. It's just a demo to show you. Here's how you get an answer. Okay, so now I have this function async, and I'm going to talk a little more about it in a minute, that returns a future. And that future, if we looked at its type, which we will when we run this future is a standard future of size t, or unsigned in, and so what happens here is I run this asynchronously, and now I'm going to run the same function synchronously on main, so these two are running concurrently. And now I call future.get. That's a blocking call. So if my main function finishes first, this guy is still running, I'll block until this guy finishes, because that's where I got the future from this guy. Okay, and the size t is just a count the number of times this guy went around the loop, and this is the number of times the child went around the loop. Okay? And I'll tell you how that works in a minute. So I just write them out, and I show you the type of the future. So future is important. Let's run it. So hello, main, async, async, async. Child thread wrote message 25 times, main thread wrote message 25 times. Type of future is class standard int future signed in, unsigned in. Okay? So what the future does is it gives us a way to get a result from a child thread. Okay? Win32 API doesn't do that. So, and that's a standard problem. How do you give arguments to threads and how do you get results back? And the C++11 threading library made that really easy. I just add, if I have arguments, I just pump them into my thread constructor. Okay, and if I have results, I get a future. Now here's how futures work. This function async standard async, this is a part of the C++11 library. And what this async does is it constructs a promise. And it constructs a future. The future and the promise are linked. What happens is I construct a promise, then I construct a future, and I say future.get, I say f, my future, dot get future promise. And that links the promise and the future together. And what happens is when your thread is done, it calls promise.setValue, and that tells the future unblock. That makes the future go from unsignaled to signaled, so anybody waiting on the future returns with a result. Cool. So a promise, it determines when the thread is done, and the future just blocks until the thread's done. Now, there's a tricky part. The tricky part is you can't declare the promise at the beginning of your async function that's going to run this thread, declare the future, and then in the thread function, at the end when the thread's done, have the promise set the value, because what's going to happen is if you declare the promise right at the beginning of this async function, while that thread is running, you're going to return. The whole idea of async is to run while that is still running, okay? Now that promise is out of scope, okay? And when you try to call in your thread promise.setValue, it'll throw an assertion because that guy is gone, okay? He doesn't exist. So what you have to do is at the beginning of the function, I have an example that does exactly this to show you what goes on, and I couldn't find it this morning. Somewhere, I can't find it. So, but what you have to do is, in the function that's going to do the same job as async, you declare the future, then inside the thread function, so here's my async function, and now what I'm doing is I'm creating a thread, and I'm just going to hand it the function that you passed me in the async as a callable object, okay? And so what I do is, inside the thread, I declare the promise, and then I declare a reference to the future up here that I'm going to return, and I link them. And now, then I start the thread up and immediately return the future. But the promise is going to stay good because I declared the promise in the thread function. So it isn't until I exit the thread function that that promise is going to become invalid. So at the end of the thread processing, before I exit the thread function, I call setValue. Away we go. Does that make sense? No. I will show you an example. If I can find it, I'll show you tomorrow morning. If I can't find it, Saturday I will find it and I will post it and I will put a message on Piazza, and you'll have a chance on Tuesday morning, but when we're doing our midterm review, to ask questions about it. Okay, so you'll absolutely get a chance if that doesn't make sense.
I lost you after you said when you bind the promise and the future after you call get future promise. So what happened after that?
So what happens is, that means that when I call setValue on the promise, that linking makes the future become signaled, so anybody waiting on the future will return with a result. Okay, that's all. Okay? And I will see some more. I do have a promise example. It doesn't show you how async works, and that's what I wanted to do, was show you how async works. But you will see that linking and stuff going on. Yeah. How?
Is there any other ways to get message, get result, or?
Yeah, I could have a lambda that had a capture value,
yeah,
and that now when I finish my thread, I can access the lambda, but the lambda better give me a way to block. I don't want to, that lambda may be in use in my thread, you know, after I've returned, so I have to be careful that I don't.
Do you have any examples of the lambda?
Don't know whether I do, but you know, the promise and future were designed to make that work.
Yeah.
Okay, so that's easy. And async is the easiest way on earth to get that to happen. Okay, I can pass any number of arguments I want. I pass the function, and I get the return. But you can do that if you send me an email today. I won't do it tomorrow. I won't talk about it. I won't show you an example tomorrow morning because I got to finish looking at your project ones tonight. Okay, so I can't. But this weekend, I will generate an example, and when I find I have to find the code where I've demonstrated how async works, and when I do that, I'll do your example that replaces async with a lambda, and I'll show you what you got to do to. Okay.
What I think is just like last semester's work, we use WCF to communicate from one process with another process. Can we just do within the WCF to get data from a thread?
That would be that could be dangerous. Okay, so I mean, you definitely can post messages from a child thread to a parent thread safely with a queue, but you know that's a lot of mechanics, a lot of infrastructure. If you have a communication channel, absolutely the right thing to do.
Okay.
If I want to talk between two processes, absolutely the right thing to do. But here, you know, when I'm just communicating between, you know, in a little tiny program between two threads, then that's a huge amount of stuff. That, you know, that's all. But all of those schemes work. You send me an email, and I will. Won't be until this weekend, but I'll do a lambda example. You know. So anyway, so let's just run it. Did I already run it? Yeah, I already ran it. So there we go. So you know, it's telling you it got the values and telling you about the future. So that's the future. Let's look at promise. So this is part way to what I was looking for and couldn't find. This shows you the linking between promises and futures, but it doesn't really show you everything that the async does. So here in this function getAnswer, I'm passing a promise by reference. And thread is thinking, sleeps for a second, and then p set value, the answer is 42. Okay? So get another answer, standard promise by reference. So the reference is here so that, you know, when I set the value, the caller outside will see the value set. Okay? P set value, the answer is 42. Now let's see what main is doing. So main says it declares a promise, and then it says standard future, and I'm going to return a string, F1, this is the name of the future, P1.getFuture. I've now linked F1 to P1, P1 to F1. Okay? And now when I call, so now I say standard thread T1 get answer standard ref of P1, so I'm passing P1 in by reference. Okay? And now in the thread, when I call set value, okay, that's going to, when I call get, that's going to release that. See, I block on this get until that promise sets the value. So this is a good part of what async does, but it's not quite the whole story, because the whole story is getting that promise to stick around long enough. So yeah, I did it this way.
So The difference between this code and async is that the promise is declared inside.
Yeah, promise is declared inside
Inside the
async.
thread.
You don't have to know anything about a promise. All you have to know about is futures to use async. Okay. It helps your mental model to understand that that's what's going on. But. So, you know, so let's just get an answer. Okay. Meaning of the universe is 42. Okay. All right, so where are we? Let's see where we are. So I've talked about future, lock guard, promise, lifetime thread parameters, asynchronous methods, atomics, basic threads. I'm not going to talk about call once. It's not all that interesting. So condition variables, I'm going to talk about in the context of the blocking queue. So I won't look at that here. So, and we've looked at, I want to look at futures, but before we do that, let's take a quick look at task. There is something called a package task, which doesn't do much more than future async. I have never used package task. It does the same thing. You know, async to me is just easier. You know. There's one less step you do with package task, but I'm not a big fan of package task, so package task won't be on the midterm. There's a lot of stuff. I won't tell you whether it's going to be on or not, but package task won't be on the midterm. Okay, so, but let's look at futures. Now, here I'm going to use the file system, so let's see what's going on here. So, you know, to use futures, I need to pound include future. So to use async, I need to pound include future. And I'm using the file system, you know, what I put in. So here's a search. This search is for a text string in a file. So I pass in a file name and the text string, and what I'm going to do is read out of the file, and I'm going to insert what I read out of the file into a string stream. So, you know, you don't need to be terribly concerned about it. A string stream, I haven't talked about that much yet, but a string stream is just an in-memory string that has a stream interface. So I can insert into that stream. And when we talk about the standard I/O, I'll show you that there's a readbuff class that's internal to those sources, and I could just stream everything, you know, just one stream, bam, you know. But anyway, that's what I'm doing. I'm just filling up, from this file, I'm filling up this in-memory string, and now I say string contents equals temp.string. I'm getting this, the standard string out of the string stream object, okay? And then now I'm going to find the text, okay? And so contents.find, and you know, I've got a find function here. Find, no, I'm just using a string find. I'm sorry, I'm just using a string find. And so as long as, you know, I didn't get to the end of the file, then, and now what I'm returning is the name of the file. So if I found the text in the file, I return the name of the file. If I didn't find the text in the file, I return an empty string. Okay? Just the protocol I'm using, this little example. Nothing particularly important about that. And so now I say files using my file system directory, get files, get on. So what I'm doing is I'm getting files out of the project directory, the header files, and So in files, I get all the header files, and in more, I get all the CPP files, and then now I'm adding them together. Okay. So I have a list of all of the files that are either header files or CPP files. And now in main, I create a search string that says pound include, and files containing the string. This is a, okay, yeah. So, so here, so let's skip over the sequential search, just here to show you what you do. So now, here I say, standard vector of standard future of strings, futures, files.size, okay. So, so this is just, I'm creating an array of, what I'm really doing is creating a standard vector big enough to hold all of those file names, however many elements are in files, okay. It was the same thing if I'd said reserve. Okay, yeah, I can give a number in the constructor, and it does a reserve. Okay, so now, after searching files outside the, files for a string, and I print out the string, so now I'm going to sequentially display. So I say string out futures of I.get. So what happened here is, in this vector, I just went around here for every file in my files, and now I say futures of I equals standard async search files of I search string. So I have a whole bunch of these searches going on concurrently. Not a whole bunch, because it turns out I've only got 3 files. But if I went up a couple of layers, I might have 50 or 60 files, and they would all run concurrency. I would search all that concurrently. Okay. So, and now I just come to the get. So while this is a blocking call, an awful lot of processing has happened asynchronously. It's entirely possible by the time I get the get, everything's done. Okay. So now, let's just run it. So this says, files containing the string pound include, after searching three files for string include, all of these have pound include. Now let's just go and change this to main. And run it. And now only the CPPs are shown, because they're the only ones with main. Okay. Of course, if I went in a comment, put main in my header file, I would have. Okay. But anyway, so nice way. So async, I can use async to get a whole bunch of concurrent processing going on. So asynchronously means that the calling thread called this function and returns almost immediately, just did whatever it needed to do to start a thread and then returned immediately. And so that thread processing is going on while that function is returned. That's asynchronous processing. Concurrent processing says these things are guaranteed to be going on at the same time. And I happen to be doing that by, for every element, for every file name in my collection, I am, wherever my async function was, I am just doing all of these. This is now parallel. Okay. If I run once, that's an example of asynchronous processing. If I run it, in this loop like this is an example of parallel processing. Okay. Who needs a parallel library? It's so easy to write. So easy to write. Okay, so let's see where we are. I think I've done everything I want to talk about. We've parameters, lifetime, promise, lock guard, futures, future, condition variables we'll talk about in a minute, concurrency. I'm not going to, callback isn't terribly interesting. You can look at it and you know, basic thread. So we've looked at all of this except for call once and condition variable. And to look at condition variables, we are going to look at, oh, before I do that, I want to do one thing. For Mr. Wong, I want to do callbacks. So, so here is an example of callbacks. This little toString function, you've seen me use it. All I'm doing is I'm going to use it to convert an integer into a string. Okay, so I insert into a string stream, and this insertion automatically converts whatever this type is to a string sequence of characters, because that's what's, you know, that's the only thing the console can display is characters. So, and then I return the string. So, and now my thread proc accepts. So here's a template type name CB callback. This is a function, callback function, and a count. I'm going to pass it an argument count. So here, this is the function that the thread is going to run. And so what it's doing is it's child thread number, and it's just taking this, it's incrementing this count as we go, wherever I did it. And am I not incrementing it? I don't remember. But anyway, so this thread is working, and then I sleep for a while. Now, at the bottom, I call callback. Okay? So, and now I have a callback function that says another function, and I'm going to come back and talk about this in a minute. I have a lambda that says calling back. And I wanted to show you that this thread proc can take either lambdas or ordinary functions. Okay. And you see something strange here. What's this decal type? Decal type. So what happens here is, because this is a lambda, and I haven't attached this to a standard function, this has a weird unknown type, a type the compiler made up when it compiled this. You can see the name of the type if you do a type ID on it, but you know, it's not supposed to be anything that you handle. But here, my thread proc needs to, its type inference isn't strong enough to figure out what callback is. It needs some help. So what I say here is decal type of callback. Okay, so this is the type. Decal type is the type that I am declaring. Okay, so what's here is I've said I'm passing into you thread a thread proc whose argument is a decal type. Decal type, I have this expression, auto callback. Decal type is whatever that type is. I don't know what it is, but compiler, you know, that's the type I want you to infer here. That's a bit of template metaprogramming. This is happening at compile time. That type definition, that type inference happened at compile time. That has to happen. That's part of template deduction. There's a lot of type deduction that happens as templates are expanded. So, so I have told it that's the type, and now I give it this callback, which is a lambda. Now I'm going to give it this function pointer callback. Callback function, okay? And I used decal type here, but I would have been perfectly happy if I'd used a function pointer, you know, just said whatever the type is, void, whatever, you know. And now, but forget the join all for a minute. So now I've started these two threads and they're running. They're going to print a bunch of messages and then do a callback. So let's run it, and then we'll go back and talk about the other things that we saw. So another callback, calling back. And it turns out the second one I started called back before the first one that I started. Just that's an undeterminate, it's non-deterministic. The timing you can't tell. Just depends on who went to sleep when and what happened. Okay. So I'm making a callback, and you can look at this. So now let's go look at the code, and you say this is stupid. All I'm doing is on my child thread, I run the child processing, and then I run the callback on the same thread. Why didn't I just make it part of the child processing? It's stupid. But it isn't. Here's why. Imagine that I haven't posted it yet, but in my NoSQL database, I've created, you remember I had a template method to make queries? I now have another template method to make async queries. And there, I didn't do it this way, but this would be a great place to use callback. So the thread function is the query, and the callback defines what you want to do with that query. So the query is going to return a set of keys. And I might want to one time display them, another time I might put it in some memory structure, another time I might want to do, search them or something. Okay. So the callback, what happens when you use callbacks, it's always the point is that you're defining the main thread processing to do something, and you're defining the callback to do some different thing, and that might be installed by an application. Very often, the thread processing is defined by a library, and the application provides application-specific callbacks that say, when you're done, give me this result, or do this with your result. It's another way to get a result. It's not really the parent thread getting the result, it's the parent thread telling the child thread what to do with the result. Isn't that interesting? So, futures let us get the result from the child thread. Callbacks lets the parent tell the child thread what to do with the result. And we'll be polite here. We won't tell it to do something obnoxious. Okay. Now, there's some other stuff going on. What's this join all stuff? So, standard thread, but join all. There isn't a join all method. There isn't a join all method, except I made one. So let's look at this first one. Template type name void join all with a single argument, and all it does is, if it's joinable, it joins it. Cool. Okay. Now let's look at the second one. The second one says, I have the first and more. So this is type name T, could be, could be any name you want. Type name dot dot dot, no space, args. Now what's happening here is void join all of T first and args. So now I had so what I do is I have this list, and the first one, here's the first, and now here's the remaining, okay? And now I say, if first joinable, first.join, join all of standard move of args. So I stripped off I did the first one, stripped it off, and now I'm doing it on the, so I had a list, I did the operation on the first one, and then I called that function that takes the list with what's left. And I keep doing that, and the list gets shorter and shorter and shorter until I get to the last one, only one. And because this is a template, this is a specialization. And so the language guarantees me that given a choice between these two, if you match your specialization, take the specialization. Now, I wrote this. When I wrote this, it took me 3 times to get it to work. The first 2 said compiler error. Can you imagine what happened? This is a recursive call. I left off the stopping condition. I forgot to put the stopping condition. And so it recursed until it blew its tables bam, I'm dead. And it told me, internal compiler error, I'm dead. Okay. You managed to kill me. Okay. That's another, when we do a build server, that's another reason why you might want to build another place. I figured out how to get C# to kill the compiler, but I can kill a C++ program, in both cases by infinite recursion. I can have a header file that includes another header file that includes the first header file, so it just goes around. You know, I kill the preprocessor in the first case. In this case, I'm killing the compiler itself. But anyway, so this is called a variadic template function. And you can have variadic templates with classes as well. I'll talk about this a little more at the end of the course when we talk about template metaprogramming. This is really, this recursion happens at compile time. The compiler is forced to do this recursion because what happens is templates are resolved entirely at compile time. And so what happens is, you know, it's evaluating itself, join all, and the next thing it sees is join all. It's got to recurse. So I have written a program that runs at compile time. You can't do this with C# and Java because they don't have specialization because they don't run at compile time. They're really runtime artifacts. And so, you know, they do syntax checking, but they don't do any compilation like that. So you know, that variadic, I can take any number of arguments in that function. I can say join T1, T2. Now, I did have this little clumsiness. I had to standard move my args and standard move my threads here. And the reason for that is I can't copy, you know, this accepts copies normally. I can't copy a thread because it's not copyable. It's movable, but not copyable. And so I had to do a standard move to get this to work. On the join, I'm not passing, you know, it's just a member function of that thread, and so I'm not copying anything. You know, that's why that works so easily. But anyway, join all. Cool. Variadic templates, cool. So let's look at blocking Q, and that will finish us up for today. Okay, we got to go get it. Blocking Q. So my blocking Q class has a DQ function, an NQ function, a front just to peek at what's at the front without popping it, clear, what's your size. It's based on a Q, but also uses a mutex and a condition variable. And we'll see all about that in just a second. So let's start, first look at NQ, because that's the simpler of the two. So here's NQ. So NQ takes a standard lock on this mutex, and this mutex is a data member of the class, and so it is shared. Okay? Shared. Every member function shares that mutex. So I take a lock, and I'm doing this inside a little anonymous scope, so, you know, you could argue, you know, use a standard unique lock. And I think that I wrote this probably before I knew how the standard unique lock, but I knew this would work, so I used this. But anyway, so I push, come out of the lock, and then I notify the waiters that something is in the queue. This sets a condition. This says the condition you were waiting for has been satisfied. There is something in the queue. I have my base operation, you know, I'm using the standard queue as the basis for my queue, and that standard queue, if you try to dequeue, if you try to pop it when there's nothing in it, it'll throw an exception. Don't want that to happen. I want it to block. So let's see how we get it to block. So here's the end queue. So now, if there's something, if there's something in the queue, so up above I've taken a lock. So here I enter this lock. So I'm in this lock section. So I can safely ask, are you greater than 0? And even if I fall asleep here, it's okay because I'm in the lock. And so if it's greater than 0, then I get the front and pop the queue and I return. I'm done. But if it isn't greater than 0, now while queue size equals 0, this is if the queue is empty, I'm not satisfying the condition. Critical condition variable dot wait, and then return queue size greater than 0. So it's waiting on this condition. Queue size is greater than 0. So what it needs here is a predicate. You can give it any predicate you want. And now, so what happens is when the enqueuer calls notify, this wait returns. Great, condition satisfied. But it turns out that there are rare spurious returns from condition variables. That happens on Windows, it happens on Linux, it happens on Unix. They all have. Man pages say it happens, Windows docs say it happens. They may return without that condition being satisfied, and I'll talk about that in just a second. So you need to sit in this loop. Okay, remember I'm locked, so nobody else can sneak in ahead of me. No race condition here at all. I'm locked. So I just keep waiting until if this is not true, then I know that my wait was successful. There is something in the queue. I'm locked, so it's okay to do that. And then I grab the front, pop it, return. And you say, but you're waiting inside that lock. That's a deadlock. Beautiful way to get a deadlock to happen. Just wait inside a lock. Condition variable was designed to handle this case. It's trying to avoid race conditions. So what happens is when the thread that's executing now, the current thread is executing, when it calls cv.wait, the operating system suspends it, releases the lock, so that the enqueuer can now acquire the lock. When the enqueuer calls notify, the operating system acquires the lock. If he called notify inside the lock, then he'd have to wait for the notifier. But there's no harm doing it the way I did it. It works just fine. So now the operating system acquires the lock, gives it to that sleeping thread, and wakes him up. So I can wait because of condition variables. That's the only time you can ever do this and have it work. Condition variables were designed to make this work. I can wait inside a lock. So you could use, in the old days, I used an event to, and you can do that. But what happens is you can't wait inside the lock, so you got to wait just outside the lock with an event, and the enqueuer triggers the event, okay? And almost always it works just fine. But every once in a while, just as you've come out of that event, the event has become signaled, and so you're falling through. Your time slice expires. Bam! You go to sleep. Another thread sneaks through, grabs that entry in the queue, goes away. Now the queue is empty. You wake up knowing that there's something in the queue because you passed the test, and you call, and you throw an exception. That happens once every 10,000, 20,000, 30,000 times that the queue works. And so you test it. Great, it's working, ship it to the customer. And a month later, it's pounding on your door. You idiots, you can't write code. What's the matter with you? Okay? Because of that race condition. These spurious returns are race conditions, but the operating system makes them benign. As long as you call this, you're okay. Guaranteed to work. And I did the same thing with there is a way to take the queue and make it benign, to take the event and signaling and make that benign. But things get really complicated because of caching. Okay, you can get yourself into a hurry and a trouble with into trouble in a hurry with that. So this takes care of all that. This is the right way to do this. The library and the operating system have taken care of that caching. They flushed, or reloaded before, flushed to memory or reloaded back from memory before doing what they need to do. So, and now you look at this, and every one of these functions has a lock, unique lock, and they all use the same mutex. That mutex is a data member of this class. Okay, here it is. So it's shared by all those functions. So everybody's using the same mutex. That's critical. That's a standard programming error with threads. You got two threads that are using locks, but they happen to be using different locks. Sorry, no lock. I'm not telling you that, but this is not got a lock. Okay, so, that's the blocking queue. So the wait function, it's these operating system waits. If you want to block, you got it somewhere in your code called wait for a single object on a handle of something you want to wait on. And that's condition variables doing it. It's hiding it from you, but that's what it's doing. Somewhere down in the bowels of the implementation. So that's blocking queue. Blocking queue is a safe, effective way to communicate between threads. We're going to use it again. I emphasize that again. I pounded on you. There's all these people that love to do remote procedure calls. Much harder to get right. Complicated threading models. Polish up your resume. Go somewhere else. Message passing. Piece of cake. You guys are doing the right thing. You have a question?
When we say the condition variable wakes up the thread, is there a way to wake up a specific thread or it just
No. So a platform might enqueue them in order. I think some do. Windows doesn't. They specifically tell you when you notify, you're going to get some thread, but there's no guarantee that it's the most recent one that acquired it or the earliest one that acquired it. I think, I'll bet my bottom dollar it's always either the most recent or the oldest, but they're not telling you because next time they may change the implementation and it'll be the other way around. So they don't want you to count on that. So they say you can't count on the order. The docs specifically say that. All righty, so tomorrow, help session, I'll return project ones. If you can't come to the help session, I will return also project ones late in the afternoon at 3 o'clock. So we'll talk tomorrow about the midterm, and then we'll talk about project one. Understand that every midterm will have a question that requires you to write threading code. And the most important thing for you to look at is the C++ concurrency folder that had all those various cases. There will be, on your exam, another question that asks you to write code. Might be related to one of the projects, might be just a interesting little question occurred to me. Okay. There will definitely be questions about principles. Everything I've told you about that I said there will be on the exam, it's going to be on the exam.
Is there a diagram?
You may have to draw diagrams. Yep, probably will.
Will callback function be in the midterm?
I don't want to tell you. Doesn't mean it will. Doesn't mean it won't. I'm just, you know. But it's easy, you know, right? It's easy.
About the process, you have given us a package named process.
Yeah.
And it shows the file, the code in your notepad.